Hey, in this video we're going to look at rational functions and analyze domain, vertical asymptotes, holes in the graph, horizontal asymptotes. First thing is, how do you know a function is a rational function? Well, I guess I'd say that a rational function is a function that kind of looks like a fraction. But the more mathematical definition is that a rational function is a function of the form f of x over g of x, where function f and function g are polynomial functions. Let's look at an example here. Let's start off with the following rational function. F of x equals x plus 1 over x squared plus a 4x minus 12. Polynomial over a polynomial. Yeah, this is a rational function. So one question we could ask, this is an old question, but what is the domain? Well, remember, you can't divide by 0. So are there any values that could go in for the variable x that would produce 0 in the denominator of this fraction? Well, the answer is yes. Here's how we determine it. Take the denominator, this is all kind of review, set the denominator equal to 0. Hopefully this factors, I really don't feel like using the quadratic formula. X, I think it factors to that, plus 6 and minus 2. So you set each factor equal to 0, and you get negative 6 and 2. Those are the two values of x that makes the denominator 0. So those are the two values of x that would not be in the domain. So to write this in interval notation, you can use any number you want. You can put any number you want in for x, from negative infinity up to negative 6. Do not include negative 6. Then any number from negative 6 to 2. Do not include negative 6, do not include 2. And then any number from 2 to infinity. So that's the domain of the function. Let's review one more thing. That was reviewing domain. The next thing, how about if you're asked, to find the x and y intercepts. Find the x and y intercepts for the graph of this function. Well, remember, to find the x-intercept, you're going to let y equal 0. So you put 0 in here, and you get 0 equals x plus 1 over x squared plus 4x minus 12. Now the only time a fraction, that looks like a fraction, so go ahead and call it a fraction. The only time a fraction is equal to 0 is when the numerator is equal to 0. There's the x-intercept. So we know the graph of this beastie has an x-intercept at negative 1, 0. How do you find the y-intercept? That's right. To find the y-intercept, you let x equal 0. So put 0 in for the x's, and you'll get 0 plus 1 over 0 squared plus 4 times 0 minus 12. 0 plus 1, well, that's 1. 0 squared 0, 4 times 0 is 0. 0 plus 0 minus 12 is negative 12. So the y-intercept is negative 1/12. So the y-intercept occurs at the point 0, negative 1/12. So really, nothing new was asked here. We know how to find domains of functions. We know how to find x-intercepts. We know how to find y-intercepts. So when we come back, kind of laying the foundation for the graphing of these rational functions. So the next thing I'm going to do is I'm going to discuss the difference between a vertical asymptote for the graph or a hole in the graph. Alright, here we are next. We're building up to, eventually we're going to graph these rational functions. So I've given you a rational function, x plus 1 over x squared plus 4x plus 3. And quite simply the question is, where does the graph of this rational function, where does the graph have a vertical asymptote, which that would be like a dashed line that the graph would not cross, or where does the graph of the rational function have a hole in the graph? And a hole in the graph is just that. The graph would come along, there would be a hole, and then it would keep going. The key to determining the values of x where you would have a vertical asymptote or a hole, it goes back to the domain of the function. Whatever numbers are not in the domain, one of two things will be happening. If it's not in the domain, you're either going to have a vertical asymptote or you're going to have a hole. So just think about if you were asked to find the domain of this function. You'd say, okay, well, what values of x makes the denominator 0? So let's do that. What values of x makes the denominator 0? Well, this factors to x plus 1 times x plus 3. Here are the two values of x that makes the denominator 0. These are the two values of x not in the domain. The domain of this function is negative infinity to negative 1, parentheses around both, union with negative 1 to 3, parentheses around both, union with 3 to infinity, and parentheses around both. So these numbers are not in the domain. The graph of this function at these two values of x, one of two things will be happening. You're either going to have a vertical asymptote or you're going to have a hole in the graph. Here's how I determine whether or not you have a hole or a vertical asymptote. These are the values of x that makes the denominator 0. Simply do the following. Take this value of x, toss it into the numerator. So take the value of x, toss it into the numerator. If when you take that value of x and you toss it into the numerator, you get a result of 0, and we do here, negative 1 plus 1 is 0. When that happens, there is a hole in the graph. If you take a value of x, like this, negative 3, this makes the denominator 0. If you take that value of x and toss it into the numerator, and you do not get 0, and we don't here, that's where the graph has a vertical asymptote. So maybe you have to write this down to kind of summarize it. The process, classifying whether or not you have a hole in the graph or a vertical asymptote. The first thing is you're basically finding the domain. So that means you're going to find the values of x that makes the denominator 0. For those values of x that makes the denominator 0, take the value, toss it into the numerator for x. If you get a 0 in the numerator, you got a hole in the graph. If you don't get 0 in the numerator, that's where you have a vertical asymptote. And so that's it for the difference between a vertical asymptote and a hole in the graph. Next up will be the horizontal asymptote. All right, we've just looked at how you find the difference between the vertical asymptote and a hole in the graph. Next up is the horizontal asymptote, and I break it into 3 cases on finding horizontal asymptotes. So the first case is if the degree of the numerator is equal to the degree of the denominator, then your horizontal asymptote is the line y equals leading coefficient of numerator over leading coefficient of denominator. It's pretty straightforward. Case number 2, if the degree of your numerator is less than the degree of your denominator, then the horizontal asymptote's the line y equals 0. That's also known as the x-axis. And then case number 3, if the degree of your numerator happens to be larger than the degree of the denominator, in that case, you're not going to have a horizontal asymptote. It just doesn't exist. There'd be something called a slant asymptote or an oblique asymptote, and I'm not going to worry about that. I'm concerned with my horizontal asymptotes. So I have up here a quick example. Determine the horizontal asymptote for the graph of, and here's the first rational function, x over x squared plus 3. So what's the horizontal asymptote? Well, notice that the degree of the numerator is 1, the degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator. That means the horizontal asymptote is the line y equals 0, also known as the x-axis. Let's try one more. I have enough space here to try one more. How about the function? The rational function 3x squared minus a 2x plus 1 over 4x squared plus 2x minus 1. Notice the degree of the numerator is 2. The degree of the denominator is 2. So the degree of the numerator is equal to the degree of the denominator. When that happens, the horizontal asymptote is the line y equals leading coefficient of the numerator over the leading coefficient of the denominator. That's all there is to finding horizontal asymptotes. So when we come back, we're going to do one example of actually sketching the graph of a rational function. We're going to kind of put all of this stuff together. So that's the next example. Come on back for it. Alright, here we are. We're going to put everything together that we've talked about so far with rational functions. And we're going to sketch the graph of the rational function f of x equals x plus 3 over x squared minus 6x plus 8. First thing I do is I identify my asymptotes. Probably the easiest one to do straight away is the horizontal asymptote. Because the horizontal asymptote only requires me to compare degree of the numerator to degree of the denominator. Notice the degree of the numerator is 1, the degree of the denominator is 2. Degree of the numerator is less than the degree of the denominator, so my horizontal asymptote is the line y equals 0, also known as the x-axis. Now let's identify vertical asymptotes. So remember, for the vertical asymptotes, the key for that lies in determining the values of x that makes the denominator 0. Matches up with the domain of the function. So let's see what makes the denominator equal to 0. Well, I hope this factors. Let's see, an x here, an x here. It does. Factors to x minus 4 times x minus 2. So we get two values of x that make the denominator 0. Those are two values of x that are not in the domain. Those are two values of x that one of two things is happening for the graph of this rational function. We either have a vertical asymptote or we have a hole in the graph. So remember what I need to do next. I need to take this value of x, it makes the denominator 0, and see what it makes the numerator. So if I put 4 in for x in the numerator, my numerator would become a 7. That is not 0, so that means this is a vertical asymptote. When I take this value of x that makes the denominator 0, and I toss it into the numerator for x, I get 5. That is not 0, so that means this too produces a vertical asymptote. So I'm kind of putting the pieces together here. Let's try to do one more thing and let's find the intercepts. So let me come up here and let's find the y-intercept. So remember, to find the y-intercept, you're going to let x equal 0. So you put 0 in for the x's. And you get 0 plus 3, that's 3. 0 squared is 0. 6 times 0 is 0. 0 minus 0 plus 8 is 8. So the y-intercept is 0, 3/8. Let's find the x-intercept. Remember to find the x-intercept. You're going to let y equal 0. Okay, like I did in a prior example, I would take my rational function and I'm setting it equal to 0. Y is 0. The only time a fraction equals 0 is when the numerator is equal to 0. So what value of x is going to make the numerator 0? That's right, -3. So my x-intercept is -3, 0. I think I might have enough information right now to sketch the graph of this rational function. Let's try it. Let's see. So here we go, the x-axis, the y-axis. Yeah, that's the origin. Get some scaling on here. And, hey, let's plot our intercepts while they're right here in front of my face. So we have an x-intercept at -3, 0, a y-intercept at 0, 3/8. So I'm going to say, that's about right there. And we have a vertical asymptote at x equals 4 and a vertical asymptote at x equals 2. So a vertical asymptote at x equals 2 and a vertical asymptote at x equals 4. Maybe I need to find a few more points to get a good graph here. I have a good idea of what's happening in certain pieces of the graph. In other words, I have a good idea that from here to this vertical asymptote, the graph is doing this. Because a vertical asymptote, it's not going to cross that. It's going to get close, it's going to approach it, it's going to try to touch it. But I have a feeling it's doing this. I don't think it's coming and doing that because there would be another x-intercept. I didn't find another x-intercept. I only found one x-intercept. I don't know what's happening in here, and I'm really not sure what's happening out there, and I'm pretty sure that the graph is going to have to come this way to hit the x, or to hit that x-intercept. But what does it do after that? You know, does it cross and then come back up and hug? Because that's my horizontal asymptote. So I think what I'm going to do is just find a few more points. And that should be enough to tell me what's happening. So let's start off by analyzing what's happening between the two vertical asymptotes. Notice the number 3's in there. Well, let's see what happens if I toss 3 in for x. Let's see what number comes out. So I'm going to have to, because I'm going to need more board space, I'm going to have to erase the work we did here in finding, our horizontal and vertical asymptotes. So here it goes. So if x is 3, let's see, that will give us a 3 plus a 3 over a 3 squared minus 6 times 3 plus 8. So that's a 9 over 9 minus 18 plus 8. So that is, see, 9 minus 18, that's -9. -9 plus 1, or -9 plus 8 is -1. Oh boy, look at that, we're going to get -9. So when x is 3, our y value is -9. Ooh, unfortunately that's kind of, it's way down here. it's off my, it would be off my board. All right, well that gives me 1 point. You know, I kind of have an idea what's happening in there. But if I wanted to, you know, I could put, you know, pick a number in here like 2.5 and toss that in for x to see what comes out. And 3.5, toss that in for x and see what comes out to give me 2 more points to plot. But see, I know the graph can't come up here and cross the x-axis, or it can't come through here and cross the x-axis, because I only found one x-intercept at -3. So I'm having a decent idea that the graph is going to be hugging the vertical asymptote. So it's going to be hugging the vertical asymptote, kind of come up here, pass through that point, and then come back down, and it's hugging that vertical asymptote. Let's try to figure out what's happening to the right of this vertical asymptote. Remember, this vertical asymptote's at x equals 4. So let's put 5 in for x and see what's happening. So we put 5 in for x, and we get, okay, I'm going to cut some steps out here. 5 plus 3 is 8. The denominator, 5 squared is 25. 6 times 5 is 30. So 25 minus 30, 25 minus 30 is -5. -5 plus 8. -5 plus 8 is 3. So when x has a value of 5, y is 8/3. Well, that's almost 3, so that's about right here. Now, I definitely have a good idea of what's happening for the graph to the right of this vertical asymptote. See, the graph has to be hugging this vertical asymptote. It's going to go through that point, and then it's going to hug the x-axis, because remember, the x-axis was the horizontal asymptote, y equals 0. The only thing I'm unsure of, I mean, I have a pretty good idea that the graph right here at this x-intercept, it comes through the x-intercept, and it's going to come down below the x-axis a little bit, then it's going to come back up and hug the x-axis. Because remember, the x-axis is a horizontal asymptote. I'm pretty sure it's going to do that. I don't think it could come down here below the x-axis, then cross the x-axis, and then hug. Because if it crossed the x-axis again, that would be another x-intercept. And again, how many x-intercepts did this graph have? 1. Only 1. So I'm pretty sure it's going to come below the x-axis. I'm not sure how far, but then it's going to hug the x-axis. It's always going to be negative. It's always going to be below the x-axis over here. And if you wanted to, you could check that real quick. Take a number to the left of -3, say -10. Put -10 in for x. So you put -10 in for x, the numerator becomes a -7. The denominator would be 100 plus 60 plus 8. That's 168. -7 over 168, yeah, that's a negative number. So this is kind of a nasty one to graph, because there was a lot going on. I have a rough sketch. You know what I would do next? I would look at my graphing calculator to see, you know, how good my rough sketch is. The one thing you have to be aware of on the graphing calculator, sometimes it may put lines in here that aren't really part of the graph. I mean, those are vertical asymptotes. But that's it for putting all of this together, and hopefully it was making sense. So that's kind of like a quick rundown on the wonderful world of rational functions. Thanks for watching.